Okay, here we are. It's part 2 of sound notes. Continuing on. Now we're going to talk about some forced vibration. Sounding boards are an important part of all stringed musical instruments because they are forced into vibration and produce the sound. An unmounted tuning fork makes a faint sound. Strike a tuning fork while holding its base on a tabletop and the sound is relatively loud because the table is forced to vibrate. Its larger surface sets more air into motion. A forced vibration occurs when an object is made to vibrate by another vibrating object that is nearby. The vibration of guitar strings in an acoustic guitar would be faint if there weren't transmitted to the guitar's wooden body. The mechanism in a music box is mounted on a sounding board. Without the sounding board, the music box mechanism makes is barely audible. When the string is plucked, the wash tub is set into forced vibration and serves as a sounding board. Why are sounding boards an important part of stringed instruments? Because they make the sound louder. They amplify the sound. An object resonates when there is a force to pull it back to the starting position, enough energy to keep it vibrating. If the frequency of a forced vibration matches an object's natural frequency, resonance dramatically increases the amplitude. You pump a swing in rhythm with the swing's natural frequency. Timing is more important than the force with which you pump. Even small pumps or pushes in the rhythm with the natural frequency of the swinging motion produces large amplitudes. If two tuning forks are adjusted to the same frequency, striking one fork sets the other fork into vibration. Each compression of a sound wave gives the prong a tiny push. The frequency of these pushes matches the natural frequency of the fork, so the pushes increase the amplitude of the fork's vibration. The pushes occur at the right time and are repeated in the same direction as the instantaneous motion of the fork. I will show you examples of this in class. The first compression gives the fork a tiny push. So whenever that happens, the fork bends. Then the fork returns to its initial position. But it keeps moving and overshoots it in the opposite direction. When it returns to its initial position, the next compression arrives to repeat the cycle. So it does this over and over again. It will originally get hit, it will crush in on itself, it will then expand back out, it will overexpand and then come back in enough time for this all to happen again. If the forks are not adjusted for matched frequencies, the timing of the pushes will be off and resonance will not occur. When you tune a radio, you are adjusting the natural frequency of its electronics to one of the many incoming signals. The radio then resonates to one station at a time. So when you're trying to find your radio station, now we have all digital dials where you just hit a button and it finds it. But before, you used to have to turn the dial to try and tune into the radio stations. Resonance occurs whenever successive impulses are applied to a vibrating object in rhythm with its natural frequency. The Tacoma-Narrows Bridge collapse was caused by resonance. Wind produced a force that resonated with the natural frequency of the bridge. Amplitude increased steadily over several hours until the bridge collapsed. If you want to Google the Tacoma-Narrows Bridge, there's some really good video of this bridge wobbling back and forth. What causes resonance? When natural frequencies match. When constructive interference occurs with sound waves, the listener hears a louder sound. When destructive interference occurs, the listener hears a fainter sound or no sound at all. Sound waves, like any waves, can be made to interfere. For sound, the crest of a wave corresponds to a compression. The trough of a wave corresponds to a refraction. When the crests of one wave overlap the crests of another wave, there is constructive interference. When the crests of one wave overlap the troughs of another, there is destructive interference. Here's a lot of examples of this. Both transverse and longitudinal waves display wave interference when they are superimposed. If you look here at all of these two waves are identical to each other. When they meet up, you're going to get higher amplitudes. That's higher areas, so they're going to be louder. And then for B here, you see when they meet up for compression, for longitudinal waves, you're going to get louder. Then if you look at these next ones here, these are opposites. This one and this one is an opposite. When they come together, basically they cancel each other out, and the same thing happens down here. So we have transverse, transverse, longitudinal, and longitudinal. A listener equally distant from two sound speakers that trigger identical sound waves of constant frequency hears louder sound. The waves are added because the compression and refractions arrive in phase. If the distance between the two speakers and listener differs by a half a wavelength, refraction from one speaker arriving at the same time as the compression from the other. This causes destructive interference. So this is when waves arrive in phase. He's going to get amplified sound. When it arrives out of phase, they're slightly out of phase, and he's going to cancel and make the sound fainter. Destructive interference of sound waves is usually not a problem. There's usually enough reflection of sound to fill in the canceled spots. Sometimes dead spots occur in poorly designed theaters and gymnasiums. Reflected sound waves interfere with unreflected waves to form zones of low amplitude. Destructive sound interference is used in anti-noise technology. Noisy devices such as a jackhammer have microphones that send the sound of the device to electronic microchips. The microchips create mirror image wave patterns that are fed to the earphones worn by the operator. Sound waves from the hammer are neutralized by the mirror image waves in the earphones. So these are also like the headphones that you wear for your music, the sound canceling headphones. It's the same type of technology. In some automobiles, noise detecting microphones inside the car pick up engines or road noise. Speakers in the car then emit an opposite signal that cancels out this noise, so the human ear can't detect them. The cabins of some airplanes are now quieted with this anti-noise technology. Ken Ford tows gliders in quiet comfort when he wears his noise-canceling earphones. I think a lot of us now own these. You can get them on the market pretty easily. What are the effects of constructive and destructive interference? When two tones of slightly different frequencies are sounded together, a regular fluctuation in the loudness of the combined sound is heard. When two tones of slightly different frequencies, so these are just right off, just a little bit off, are sounded together, the sound is loud, then faint, then loud, then faint, and so on. This periodic variation in the loudness of sound is called beats. Beats can be heard when two slightly mismatched tuning forks are sounded together. If you look here, they're not right in tune with each other. This is where they overlap, but then they're off, get destructive, they're off. This is where it kind of sounds like wow, 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 wow. If you're in choir or you play a musical instrument with others and you're trying to tune up with each other and everybody's supposed to be playing the same note or singing the same note and somebody's slightly off, you can hear this. The vibration of tuning forks will be momentarily in step, then out of step, then in again, and so on. When the combined waves reach your ears in step, the sound is maximized. When the forks are out of step, a compression from one fork is met with a refraction from the other, resulting in a minimum sound. The sound that reaches your ears throbs between maximum and minimum loudness and produces a tremolo effect. Walk with someone who has a different stride. At times you are both in step, and other times you are both out of step. In general, the number of times you are in step in each unit of time is equal to the difference in the frequencies of your steps. This also applies to a pair of tuning forks. When one fork vibrates 264 times per second, and the other tuning fork only goes 262 times per second, they are in step twice each second. A beat frequency of 2 Hz is heard. Representations of a 10 Hz sound wave and a 12 Hz sound wave during a 1 second time interval. The two waves overlap to produce a composite wave with a beat frequency of 2 Hz. So you see where these are the two waves as they go, but together, this is where they'll be in step with each other, and this is where they're out of step with each other. Although the separate waves are of constant amplitude, we see amplitude variations in a superimposed waveform. This variation is produced by the interference of the two superposed waves. Maximum amplitude of the composite wave occurs when both waves are in phase. Minimum amplitude occurs when both waves are completely out of phase. If you overlap two combs of different teeth spacings, you'll see a moire pattern that is related to beats. The number of beats per length will equal the difference in the number of teeth per length for the two combs. So you see that it's got areas that it's together and areas that it's apart. Beats can occur with any kind of wave and are a particular way to compare frequencies. To tune a piano tuner listens for beats produced between a standard tuning fork and a particular string on the piano. When the frequencies are identical, the beats disappear. The members of an orchestra tune up by listening for beats between the instruments and the standard tone. What is the beat frequency when a 262 Hz and a 266 Hz tuning fork are sounded together? What about a 262 Hz and a 272 Hz? The answer, the 262 Hz and 266 Hz will produce 4 beats per second. That is 4 Hz. 262 Hz minus 262 Hz gives you the 4. The 262 and the 272 will give you 10, because if you subtract them, they'll give you 10. And here's the last question: what causes beats? And this is the end of the notes for sound.